Let's consider a coin toss. We cannot tell what will be the result in a single coin toss, but if we run, let's say, 1000 trials, by common sense the result will be close to 500 heads and 500 tails. In this case, 500 heads among 1000 trials is what we call the head relative frequency. Now let's run an experiment with 3 trials. The result was 1 head among 3 trials. If we randomly take one sample of this sample space, the probability of pick a head or tail is 33 and 66% respectively. An event can be any result or result set you previously decided. By example, we roll a dice 3 times and point out the numbers. Let's suppose we got these numbers for the trials A, B, and C. Then we use the set operations, the same way as objects, and find the union, intersection, and negation. Like in set theory, these two will be equivalent sets. An experiment sample space refers to all the result options. By example, take a single card from the 52 deck. By replacing this card and taking another, we say that the 2 cards were selected from an equiprobable space with 52 options. Now consider another experiment where you take one card and without replacing select another. This is not an equiprobable space because the first one was selected from 52 and the second from the remaining 51. Now consider the event of getting a high card. This is 12 among 52. Then consider a different experiment. Get a spade card. This is 13 among 52. The same way as in set theory, this number right here corresponds to the intersection between A and B. Denotes the probability of getting a high spade card. Now let's organize our ideas and define probability. Is a number between 0 and 1 that denotes the relative frequency of an event to happen. We obtain this factor dividing the result we want by the sample space. In a dice, any number has 1 divided by 6 chances to occur. Usually, you will find this factor represented by a percentage number. A real-world example. In a 60-person group, 30 speaks English, 10 speak Spanish, 5 speaks both languages. If you select one person randomly, find the probability that person speaks English or Spanish, not inclusively and inclusively. A Venn diagram will help us to evaluate the situation clearly. As you can see, along with the English and Spanish probabilities, there are a group of bilingual persons that cannot be included. On the first case, we want persons who exclusively speaks English or Spanish. 58%. To find this inclusively, do the same without subtract the bilingual persons. 66%. From this problem, we conclude in a union set operation, always ask if the question is inclusively or not. From Unit 4, you probably remember what does this notation means. Implies that A will occur only if B happens. Now consider 2 simultaneous dice landings. We have 36 possible combinations, and suppose we define the event A of having 5 and another event B of any dice be the number 3. Among the 36 combinations, these 4 satisfies the first event, and these 11 satisfies the second. Let's find the common elements between these 2 events, and this is having 5 with a 3 dice, the A and B intersection. So why is this intersection important? Well, what if we want to know the chances of getting 5 once a dice with 3 has landed? Let's say having 5 if 3 occurs. Here is where this formula becomes useful, 18%. The same method applies if we want to know the chances of having a dice with 3 if the result is 5. Let's say having 3 if 5 occurs, 50%. It's time to place your bets here. A coin is tossed 2 times. Find the conditional probabilities between A and B, where A is the event of getting at least 1 head, and B the event that the first point is a head. First, always try to visualize the experiment sample space. Here we are going to use 1 to represent heads and 0 to represent tails. These are all the possible combinations. Having the total sample space, now find all the possible combinations that satisfies both events, A and B, and the intersection that will be used into the formula. The first conditional probability that the first point is a head if both points are heads will be the number of elements in the intersection, 2, divided by the number of elements in the B sample space, 2. By common sense, you figure that this is 100% sure. The second conditional probability that the first point is a head if at least one of them is a head. The number of elements in the intersection 2 divided by the number of elements in the A sample space, 3. This gives us 66%. Would you place money on this bet? Event independence. In simple words, 2 events are independent if their occurrence does not affect each other. To verify their independence, just evaluate this condition on their intersection set with their probabilities. By example, you have 3 random cards, and suppose you defined E1, E2, and E3 events. Let's find all the sample spaces. By common sense, the first card color has nothing to do with the second and vice versa, but the third event needs the second to happen. Let's say event 3 happens if event 2 occurs. To have 2 red cards in a row, the second must be red, right? This can be validated with this method. The event 1 is independent with each other, but the event 3 does not satisfy the expression with the event 2. That's why we say event 3 depends on event 2. But watch out each case. In this example, the event 2 is independent from event 3. All the examples we have solved by hand until now are within small sample spaces. Now what happens if we must analyze multiple complex situations? Don't even try to organize a 20 dice landing sample space. There are billions of outcomes. That's why scientists worked during centuries on these areas and developed the concept of binomial distribution to provide you a magic formula for solving most situations. Now, when you are modeling any real-world situation into a binomial distribution case, you must have very clear the point you want to prove inside the experiment. Also, maybe you prefer to separate a complex experiment into multiple stages. In each trial, everything will be reduced to only one result, true or false. The formula involves 3 parameters, k, n, and p as the situation description. By example, we want to compute the chances of getting 5 times 1 on 20 dice landings. Here the k factor will be 5 times the target, the n factor will be 20 trials, and the p factor the probability of getting the target in one single trial. This is 1 divided by 6. The formula is a product between 3 operations. The first is a combination of n over k case, which we saw previously on Unit 5. The second is the p factor raised to the k factor, and the third is 1 minus the p factor raised to n minus the k factor. Let's solve each of the terms on the expression. In computer science, this notation is used to denote any power of 10. After solve the combination and the powers, we found that there are 13% chances to getting 5 times 1 in a 20 dice landings. Now, this result applies for every digit. After all, any of them have the same probability, 1 divided by 6. Because any landing cannot be affected by others, the order which the 5 same landings appears does not matter in this experiment, only their existence. A real-world example. Let's suppose someone proposed to double your money if you get 4 or more red cards from a 6 random set. This game seems easy to win with a little luck help. After all, 4 is the half plus 1. Let's see the real chances to win and place our bet here. First, define the parameters to use in the formula. N equals to the total number of trials, 6. P are the chances of getting a red card in a single trial, 1 divided by 2, and K will be every situation equal or greater than 4, so 4, 5 or 6 red cards. To find our chances to win, we must join the 3 scenarios on our side, so let's get each probability on 4, 5 or 6 red cards and do the summation. We found that have only 25% chances to win. In the long term, this is a big business for the house. Now, in simple words, a random variable is just the assignment of any numeric value from a sample space outcome to any identifier. It's variable because it does not have a constant value. By example, if you throw 2 dice simultaneously, the identifier Rx can be any of these outcomes, and the probability distribution of each result is clearly defined. By example, there is only one way to sum 2 with 2 dice, but as much as 5 different ways to sum 6, so 5 times more chances to get 6 rather than 2 in any trial.
Shut up and take my money!
We have to point out that nothing is certain at all. By example, in physics there is a principle called mass center that will dramatically affect a coin toss if one of the sides is unbalanced. Even coins are not 100% reliable. Expectation is a way to link and demonstrate the relation between the components for complex situations. This is useful for advanced problems like finding the probability of an event having everything else. To find it, first compute the probability distribution, get the product for each random variable with its probability and do the summation. On a 6 coin landings, we expect 3 heads. Don't worry, this is something that you can do with a simple average. In a set of elements, to get the variance, subtract each value from the average. Raise it to the square and sum all the results. Finally, divide by the number of elements, 4 in this case. As scientists, we are interested on the standard deviation, which is computed by the square root of the variance. Standard deviation is for predictability models. For example, from a group of fruits you get these samples. It is almost sure that another element from the same population will be 42.79 grams greater or less than the average. So we expect the next fruit selected within this range. Now, there is a myth we've always heard that you can approve a multiple option test just by guessing the answers. On a 5-option, 28-question test, let's evaluate 3 scenarios to discuss it. In the first case, you don't know what the hell is the test about. In the second case, you know stuff, so at least 8 questions were solved. In the third case, you know at least 4 answers for sure, and also how to identify a ridiculously wrong option for each question. In the first case, we have 1 divided by 5 probabilities to solve each question, so 0.2 chances to solve all questions randomly. Most schools require the half answer to approve. Multiplying everything by 2, this is 40%. That explains why so many negligent people have their professional degree. And in the second case, we have solved 28% of the test. Added to 0.2, this is 97% chances to approve with little effort. In the third case, we have solved 14%, and without the obvious question, the chances increase to 1 divided by 4. Finally, 78% chances to approve. On my university, the obvious question along with the test were designed to detect if the student don't know what the hell is talking about, and also could be disqualified for trying this. So I have no problem with say, sorry, I don't know the answer, and let the blank space. First question, you throw a coin along with the dice. Find the probabilities for the events 1 and 2. First, let's organize the sample space with all the possible combinations for this experiment. So, among these 12 elements, 3 satisfies the first condition, heads with even number, and 2 satisfies the second, tails with a 3 multiple. This is 25 and 16% respectively.
$20. Your move, Mr. Bond.
I'll take a hit, dealer.
Question 2. Having all this information, try to predict how's gonna be the game result. Mr. Bond is in a very bad position at this point. Let's find the exact probabilities. He loses by any number greater than 4. Without the cards in the table, this is 32 among 47, 68%. But if he reaches 21, wins the game. This is 4 among 47, 9%. Also, he can reach any number under 20, but still in disadvantage, between 15 and 23%. The probabilities of reach 20 are even lower, 6%. In my opinion, this game has finished.
What a pity, Mr. Bond.
But, well, it was Homer's fault. I didn't lose. I never lose. Well, at least tell me the details of your plot for world domination.
I'm not going to fall for that.
All right, I raise a quarter.
How about?
I'm out. I'm out. Oh. Do you want another card or not?
Huh? Oh, okay, I'll take 3.
Don't!
I mean, woohoo!
I'm in. Let's see your cards.
Oh, I was bluffing.
Come to Papa. Wait a minute. You have a straight flush, Homer.
Having all the information, let's find the probabilities to construct this flush at once, like Homer did. First, let's organize the sample space. With 25 cards in the table, there are 27 cards to select. All the players went out except Mo. This hand is an extremely lucky succession of events. The 7 from the 27, the 8 from the remaining 26, and the 9 from the remaining 25. So it will be an intersection within all 3 events. This is less than 0%, almost impossible to achieve. A little slow, but he always wins.
Go! You do this every time. Ugh, God, choking on my own words here.
Hey, don't yell at Homer. Just 'cause he's a little slow.
Something was said. Not good. What was it? They called you slow! How dare you call me that?
Hey, Homer, you still here? Boy, you are slow.
Something said. Not good.
Get the hell out of here!
I promised you a surprise today.
Wow! I knew it.
And here it is. We're going to take a test.
We have 20 multi-area tests. A total of 5 students failed maths. A total of 3 students failed chemistry. And among all, 2 students failed both. Find the following data. 1. A student is selected knowing that he failed chemistry. What's the probability that he also failed maths? This is a conditional. He failed maths if failed chemistry. 2. Another student is selected knowing that he failed maths. Find the probability that he also failed chemistry. 3. Find the probability that a random student failed chemistry or maths, inclusive and not inclusive. And 4. Find the probability that a random student didn't fail any test. First, let's define the event A as fail in chemistry and the event B as fail in maths. On their intersection we have 2 students who failed both. Divided by 3, this is 67%. The same applies for the second question. 2 divided by the number of students who failed maths, 40%. On the third question, this cannot be inclusive. Among these 2 groups, there are 2 students which intersect both. So we have to subtract their probability from the union probability, 30%. And finally, the students who approved were the 70%. This is something that we can figure out by setting a Venn diagram. On the same classroom, you select 4 students randomly. Find the probability that those 4 are among whose failed the math test. We select the students one by one and all at the same time. Check out if there are any differences. 1 by 1 is similar to the poker example. 5 among 20, then 4 among 19 remaining, 3 among 18, 2 among 17. The product is 0.1%. Now there are 5 different ways to select 4 among 5 and 4,800 different ways to select 4 from 20. The probabilities to select any of the right 5 combinations among 4,800 is 0.1%. So there is no difference to pick them one by one or all at the same time. Knowing that we have 14 boys and 6 girls in the classroom, find the probabilities to select 4 random students, that be all boys or all girls. To save time, we prefer to do this with the N over K case. Also, you can do it one by one like the poker example. 21% probabilities to be all boys and 0.31% probabilities to be all girls. Question 7. Suppose in the fog of war a shooter made a streak of 11 shots. According to the information, we want to predict the result. Find the probabilities for each case. The idea of binomial distribution will help us to solve complex situations. To find the probability to hit the target exactly 3 times, we replace each term into the formula and the number of trials. K the number of trials that hit the target, and P the probability in any single trial, 8%. To find how likely the shutter will hit over 5 times, we start with, let's say, 6 times, 23%, now 7 times, 16%, 8 times, 8%, 9 times, 3%. Doing the summation, there are 50% probabilities, and this is how binomial distribution behaves. There is no need to extend the analysis till the end. The discussion will always center in the hot spot, 5.5 in this case. On the third question, we find the probabilities to hit 0 times. So subtract from 1 will be every case that is over 0. Almost 100%. I wouldn't want to be your enemy.
Marge, you waited for me. Okay, Marge, let's go.
I'll catch up to you.
Marge, I'm taking the car.
I'll walk.
We need to talk. You're spending too much time at the casino, and I think you may have a problem.
I won $60 last night.
Woohoo! Problem solved!
8th question. How much money will earn during a month? Everybody knows how to answer by the average. The question here is do it as a probability distribution. Let's organize the sample space. It's more likely to earn $12 or $15 and a big price sometimes. Multiply every random variable with its probability and extend this pattern during a month. Almost $600 to spend inside the house. Back in the days, this was good money. Last question, according to the data, find the standard deviation. First, we need to compute the variance, and then its square root. So, each value is approximately $16.20 away from the average. This has been all for Unit 6. By the way, if you want to learn from more advanced exercises, a link will be available on the video description. Thank you very much for watching our video and see you on the next unit.